everybody, and welcome to our project. We are Team 24063, and we are working with the AME department for our project. And right now, let's introduce our team.
Falls can be dangerous and expensive. According to the CDC, 3 million older people are treated in emergency departments for fall injuries each year. Modern walkers can be vital to keeping people safe and mobile. However, they are also limited. When tasked with the project of creating a fall prevention system, our team decided to design and create an improved walker, a smart walker that could predict and prevent falls on its own. Using several sensors to indicate and prevent different types of falls, the smart walker stabilizes itself using an automatic braking system in order to provide additional support for the user. The smart walker uses several sensors and techniques to prevent and predict falls. One of the walker's attractive features is that it is designed so that the user is centered inside the walker walls, instead of walking behind it like most other walkers. This allows for additional support against sideward falls. Another of the walker's features is the wide base. The base is angled by 5 to 10 degrees on all sides in order to prevent tipping and support the user's weight in the event of a fall. The walker also has manual and automatic braking systems. The manual brakes can allow for extra control on inclines and declines, and the automatic brakes trigger to provide increased stability and support in the case of a potential fall. There are 3 sensors which predict and prevent falls. The first is force sensors located in the handle grips. The walker brakes are initially triggered to prevent movement until both hands are gently touching the handle grips. Then the brakes deactivate and allow the user to begin walking with the walker. The second sensor is a LiDAR sensor located in the front of the walker. The sensor is aimed at the user and ensures that they are centered within the walker at all times. The smart walker senses the distance between the user and the front of the walker, and if the user is not in the center of the walker for several seconds, the automatic brakes are triggered in order to allow the user to catch up to it and return to the center. The last fall detection sensor is an accelerometer, which reports any fast changes in speed, which may be indicative of the user starting to fall or the walker slipping. If a drastic increase in speed is detected, this triggers the automatic brakes as well.
Here's a brief overview of our smart walker design. So the frame itself is constructed of McMaster car aluminum extrusions, and these custom-made brackets were made to attach the frame together. Also, wheel caps were custom 3D printed to use the wheels of a walker that was donated to us from our mentor. And additionally, these spacer brackets to use the manual brakes from the walker that was donated to us. And the solenoid brakes had to have spacers made to line up with the lever arms to trigger them to come in contact with the wheel at the right location. Additionally, these custom handles had to be made, which mimic the design of the ones that were on the donated walker, but the upper section has a square cutout rather than a circular cutout. On the circular frame walker, they had circles, so we had to custom make those. Also, the battery box had to be custom made to fit the battery that we chose to power the system, and the electrical box had to be custom made to fit the electronics and the different sensors that needed to be placed on the electrical box.
Our system requirements dictate that we shall have an option to apply manual brakes, have a battery life of at least 12 hours, have automatic brakes that act within 0.4 seconds of detecting fall risk, as well as triggering the brakes when acceleration is greater than 15 feet per second squared. The walker must be able to fit through a doorway width of 32 inches. It shall not require more than 10 pounds to move. It shall minimize harm to the user in case the user falls. And lastly, it shall be biocompatible and shall not harm the user when touched. We passed almost all of our system requirements with high margins. Additionally, outside of these requirements, we tested for our walker's tipping angle and found that we outperformed conventional walkers in this aspect as well. We found the battery life to be almost 3 times the requirement. Moreover, we tested the reaction time of the automatic brakes using an oscilloscope and found it to be almost half of what was required. The resistive force, or in other words, the force required to push the walker, was almost a third of the maximum limit. And lastly, we found the tipping angle to be almost 2 times the amount of a standard walker's. This is our poster for Design Day, detailing our progress over the year.
The Smart Walker also includes an interface with the previous project designed by Hazeli Lab. Their project utilizes advanced camera settings which detect potential falls by calculating the angle between the user's center of gravity and feet. When the angle of the user's center of gravity passes a certain threshold, the user becomes unstable and will fall. When this instability is detected, Hazeli Lab Systems then sends a binary signal to the Smart Walker, which then triggers the walker's automatic emergency braking system within milliseconds, allowing the user to use the walker to stabilize themselves.
A significant barrier and hardship that the team faced was the challenges caused by the project's inherently mechanically demanding design. The team members dominantly specialize in software and hardware, while there is only one mechanical engineer. To compensate for this, the entire team had to self-teach to contribute to the mechanical design. Some of the custom mechanical parts that were created for this project were the design and construction of the entire aluminum frame and the triangular brackets to support that frame, as well as several custom 3D printed parts including the manual hand braking mechanism, automatic and manual brake attachments, electrical box, wheel connectors, and battery holder. The team worked together to overcome these challenges and design, test, and redesign these components in order to actualize the walker.
Thank you for watching our video, and special thank you to the Hazeli Lab for sponsoring us, and also thank you to Eugene, Kevin, and Merhad. We couldn't have done it without you guys, and also special thank you to our mentor, Dr. Mike. He's been a huge help throughout this process. And again, thank you for watching our project video.